Okay. Hi, everyone. My name is Kendi Otubamo. I'm a senior solutions architect here at Amazon. I work specifically with AWS partners to build ecosystem around our NoSQL database offering. I've been with AWS for about 5 years now. Kind of started working with relational database technologies like RDS, and then initially on RDS Oracle. Then I later switched to open source databases, worked on MySQL for a while, was a regional subject matter expert for RDS MySQL and Aura MySQL, and that was kind of like my introduction to open source databases. And I used to look at a lot of Percona articles back then. Percona is very big on MySQL, as everybody knows. So it's interesting to be here. I'm happy to be giving this talk today along with my colleague Doug about enabling full text search capabilities on Amazon DocumentDB with MongoDB compatibility using Amazon OpenSearch service. So with that, Doug, you want to do some intro?
Yeah, thanks, Kenny. So my name is Doug Bonser. I am a senior specialist solution architect with Amazon Web Services, focusing on Amazon DocumentDB service. So I've been at AWS about a year and a half now, but working with document databases for about 5 or 6 years. So very, very familiar with the concepts and use cases for document databases, and looking forward to sharing an example of how to use a couple of these services together.
Awesome. So before we kind of like go into the talk today, for the sake of folks that are like hearing about full text search for the first time, full text search refers to searching some text inside extensive text data and returning the results that contains one, some or all of the words from the query. So in contrast to when you are running a query on a relational database, for example, where you are trying to get exact pattern matches. Let's say you have an ID and you are trying to send a query to the database, fetch me the employee record that belongs to this ID. That is kind of like the queries that you run on your typical operational database, whether it's relational or key value or document type of store. But when we talk about full text, it's more around being able to do searches with words and search through large text fields. And then also being able to do things like adding stuff like relevance, stemming, doing things like fuzzy search. Those are kind of the capabilities that we talk about when we talk about full text. So just to kick things off, I'd like to share this quote by Werner Vogels. So according to Werner says many organizations have large collections of documents, structured and unstructured, that can benefit from a specialized search service. So if you think about it, search is a very essential part of many modern internet scale applications today. If you think of Amazon.com, if you think about Wikipedia, GitHub, all these websites or all these applications are what they are because of the ability for the users to find what they want very, very quickly. So what the broader view of what our talk today is about, doing more searching and less of, not less, but in addition to the application retrieving data from your databases, etc., there is also a lot of opportunity for businesses to include search into the application stack. So this is Amazon.com website. You can see the big search bar at the top. A lot of people actually forget that Amazon.com is also a search engine for e-commerce. So according to Retail Dive, over 50% of product searches that happen worldwide on any website, anywhere, happens on Amazon.com. So we know how to do search, and because we are at an open source conference, we are going to be talking about Amazon OpenSearch, Elasticsearch. I'll be giving a little bit of history around how things kind of happened, how we landed on OpenSearch. So before OpenSearch was launched, Amazon was doing search with a technology called A9 at some point, and then later we use technologies around Apache Solar and also OpenSearch for some of the search capabilities for Amazon.com. So the another thing to keep in mind, before we go in deeper into the talk is a lot of databases like, Postgres, for example, have full text search capabilities, which are great. Maybe let's say you just want to search through a single field. You create probably a full text index on that particular field, and you're able to run your queries. It scales up to a certain point, but if you needed to do it at the scale of Wikipedia or Amazon.com, you would need a specialized search service. And that's kind of like the crux of our talk, because again, going back to Amazon DocumentDB, there are some products that have full text search capability natively within the database, but when you need to do it at scale, having a specialized search service is the best way to go. So that kind of like brings us to modern applications and purpose-built databases. So at Amazon, we like to talk about modern internet scale applications at AWS because a lot of the problems that we solve for and a lot of the architectural patterns that we prescribe to customers are focused around being able to do things at scale. And regardless of the scale at which you are running, the economics also make sense. So talking about modern internet scale applications, the users for modern internet scale applications are usually in the millions. You have data volumes up to terabytes and petabytes. So going back to what I mentioned earlier around doing things at scale, your typical like relational database or operational data stores, they have a maximum limit of storage size, for example, that you can store your data. Some of them like 128 terabytes maximum that you could do there. We have DynamoDB, which gives you unlimited scale, but limited around being able to do analytical type of queries. So again, going back, this is why having a specialized search service is important. So performance is also very important for internet scale applications. Microsecond latency is needed. I was reading a case study about one of our customers that currently runs on DocumentDB. One of the reasons they had to re-architect their application, they were using Elasticsearch for everything, was because one of the queries they were running was returning the result at 500 milliseconds. You can imagine that's a fraction of a second. And they had to re-architect their whole application to move some stuff to DocumentDB so that they will be able to make things a little bit faster. So going back to the characteristics of modern internet scale applications and why they apply to purpose-built databases and using purpose-built databases, the access is also varied. It's not like an enterprise application that you have 100 users within the company, the HR application, something in the back end. You can easily build a monolithic application for that and you get away with it. But for modern internet scale applications, you have many mobile devices connecting. You can open a connection for each of your 1 million users to the database, for example. You also have things like IoT devices that are sending huge streams of data as well, and they are generating lots of data. So all those data, if you can't store everything within your operational data store, like your Aurora, DocumentDB, it makes sense to offload some of that data, maybe when they've been written, and move them into a search service for kind of like ongoing searching, where your search database is kind of like your archival solution in that type of use case. So the economics also has to make sense regardless of the scale of what you are doing, because if you had to throw a big server because some of these other data stores or databases, they have some deployment models where they have to be provisioned, for example, and you don't want to have to provision something because you want to do search on it when you can have a search database separately, and you can easily optimize the cost for that search pattern and then optimize the cost for your DocumentDB or Aurora or DynamoDB for that particular use case that is required for maybe for just the application read and writes. So as a result of that, typical internet scale applications have this architecture where you have your primary database and the application, the clients connect to the application code, and the application code, depending on the type of request, if it's a write, it goes to the primary database. And then if it's kind of a search request, the application knows to send that type of request to a full text index, and that could be Elasticsearch, it could be OpenSearch, it could be Apache Solr, whichever solution that you're using. And then for caching, another pattern here is that most of these primary databases usually come with streams, and any modern database needs to have stream capabilities, and DocumentDB does have that. Doug is going to dive deeper on DocumentDB streams later on in the talk. So your streams can be used to push data into all the secondary, I would say, data stores for specialized use cases, like for your caching. You could have Elastic Cache there for Redis. And then you could also use the streams as well for your analytic, like data warehousing, to push data to your data warehouse, although we don't have one here in the architecture on the screen. The demo we'll be showing later on kind of like follows this pattern, so just wanted to put it out there on a high level, what it looks like. And then some of the benefits of using this type of architecture is to be able to achieve reliability, scalability, and maintainability of your application. So your operational data store, you use that as the primary source of truth, and the application typically would be the reading and writing to that. Only your application users don't directly interact with the primary database. That would be the ideal. And then for expensive read operations, or like frequently read data, you want to put that in a cache, specialized caching service. Again, going back to the fact that the resources on your primary database is typically bounded, and you don't want to force fit everything, because a lot of customers that I work with that end up with performance issues and they have to do very complex performance tuning, I see them force fitting all the different use cases that they have into a single data store. And then you keep having to, the bottleneck keeps shifting around. Today it's a CPU problem, and then we do some query tuning, the CPU problem, then the next week it's a storage or I/O problem. When you start hitting those boundaries and the bottlenecks are starting to shift around from CPU to I/O to query tuning to statistics gathering, then I think it's time to rethink your application design and think of things that you can move out. And this is a journey that we went through at Amazon.com as well. And that is how services like DynamoDB came into the picture when we were hitting the scale of what the Oracle databases that were in place at that point in time could achieve. So with that, just wanted to give a quick rundown of the different data storage and processing systems that are available today for your relational type of workloads. it makes sense to use relational, especially for like legacy applications that have been developed like over 30 plus years on relational databases. It's kind of complex to port those kind of workloads into any other kind of data model. But you could potentially move some things out, like the key value use cases. You can move it out to like DynamoDB or DocumentDB. If you need to build new application functionality, instead of figuring out how to modify your schemas and add new columns and rewrite your code, you could build it as a separate service using some of the other specialized services. And there are also some new application development as well that also goes to relational, because that is what the developers know how to use, and the relational model is actually the best fit for that particular use case. So the other big category is the key value. When you have known static access patterns, you want to get your record by giving key. You always have the key or a combination of primary key and sort key. That fits well into the key value access pattern, and most of those key value databases also support kind of unbounded workloads. So your workload can scale to any size, although there are some physical limits there, but typically unbounded in terms of the amount of read requests and write requests that you can send to that kind of store, and also the storage size. And then the document databases provide flexible schema and have ad hoc query capabilities. You can use them as key value store as well, but they're a little bit more flexible in terms of how you can model your data. And they are also very popular with developers because you read and write data natively into them using JSON documents. Doug is going to talk more about that later, so I'll just move on to in-memory. So we have in-memory, we have graph, and then lastly we have search. So search, when you have those kind of log analytics use cases or trace analytics use cases. With the advent of microservices and the new application development patterns as well, lots of applications are generating huge amount of logs. You have many different moving parts of your application. We have Lambda functions, API gateways. Your application is not just sitting on a single server where you can just have one graph on a screen. When I used to work in enterprise IT, we had a big screen where all the major important servers, because there were just 3 or 4 that they could not go down as part of the infrastructure of the company at that time. But nowadays, your application has many moving parts, and you have thousands of microservices behind all these big applications, internet scale applications. So to be able to monitor those kind of applications, you need to have like specialized service like Elasticsearch, and we talk about the Elk stack, Elasticsearch, Logstash, and Kibana. Use Kibana dashboards. They are kind of like more purpose built and fit for those kind of monitoring use cases of highly distributed applications. And then there's also the full text search, which because I'm spending more time on the search because we are talking about search today. So for that search engine kind of capability that you want to put in your application, a search database would be more fit for that use case. So to summarize, the reasons why I consider purpose-built databases is because of 3 key things. You want to achieve scale, you want to get the best maximum performance for your applications, and because of you want to achieve very high availability for your applications. Because when you have multiple decoupled components, for example, your search, if multiple users are searching, for example, and maybe because there is a new product that was released, that shouldn't block other users that know what they want to buy. For example, on your e-commerce website, you have a separate microservice for your product catalog or for your shopping cart. So, and then the other people that are doing the search, so you are able to get higher availability for your application. So with that, I will hand over to Doug to give us talk about DocumentDB.
All right, thanks, Kenny. Thanks for that intro to the modern internet scale applications. So next, I want to spend a few minutes talking about Amazon DocumentDB, and you note in parentheses there with MongoDB compatibility. I'll explain a little bit more what that exactly means. But just focusing on document databases, why do you want to use a document database? So, there may be more reasons than this, but in general, 4 common reasons for using a document database is JSON is a flexible format. All right, we're all familiar with JSON. It's schemaless. You can just structure the documents however you need to for your use cases. Second, it's the de facto API output. Right, JSON is everywhere. It's dating myself a little bit. I mean, when I first got out of college in IT, JSON didn't exist yet, so it's you got proprietary formats, or even worse, XML with horribly heavy payloads. So, JSON is everywhere. We see it pretty much in every service we interact with, and we're familiar with it. It's easy to understand. So that makes the modeling in JSON natural, right? With scalars, you can create sub-objects in your documents. You can have arrays of scalars, arrays of other objects. So a very flexible, very natural way to model the data. And because of that, as Kenny mentioned earlier, right, with document databases, they naturally work with JSON documents, right? The JSON documents that are pervasive and everywhere and coming from all the services we deal with, you can very easily store them in a document database. So those are a couple of reasons why document databases are used, but just a few other considerations specifically around maybe your use case if you're trying to determine if you should use it or not. So certainly if you're working with JSON data, document database makes a great choice. If you need the flexible schemas, right, again, JSON data enables that. Right, enables you to change those schemas easily. So document database would work well for that if you need those ad hoc query capabilities. 2 slides ago that Kenny was showing with the different types of databases. All right, like key value database, it's geared toward you providing a key, right, and it'll give you the value. There are some ways to get creative with the keys and things like that to do some sort of secondary lookups on it, but in general, if you want to be able to look up on any field or combination of fields in a JSON document database is a good choice. Already mentioned the indexing there in relation to the queries, right? You can index any of those fields in the documents. And then lastly, operational and analytical workloads, right? So document databases are very well suited to storing your operational data that's generated as your users are interacting with the application. And then also because of the ad hoc query capabilities, the flexible indexing, you're able to handle some of those analytical workloads. So you don't necessarily have to move everything off into, say, like a data lake or something like that. You can run more complex queries on your operational data. All right, so think of it as analytical queries on the operational data in your document database. All right, so again, this is not an exhaustive list of when you should use a document database, but if you have these requirements, document database is probably a good place to look first. All right, so now that we understand, all right, why document databases are popular or good use cases for them, drill into DocumentDB a little bit. So first, talk about these 6 areas. DocumentDB is very performant, right? Millions of operations per second, millisecond latencies. So we've got many customers with very critical enterprise workloads running on DocumentDB, providing the high performance that they need. With DocumentDB, you can scale the compute and storage independently of each other, and this actually provides a lot of unique capabilities that I'm going to go into a little bit more in depth on the next slide. Right? But just know for right now, it's not a traditional monolithic database architecture where you've got the API and the query processor and the cache and the logging and the storage all on an instance or VM. The compute with the API and the query processor and the cache is separated from the storage. So got a lot of unique benefits because of that. So DocumentDB, it is simple and fully managed. Right? So as a managed service that AWS provides, you don't have to maintain or patch the underlying EC2 instances. You don't have to patch and maintain the database software running on that. The service handles that for you automatically. It is secure and compliant. So by default, it is secure in that it is what we call a VPC only service, meaning that you cannot directly access the data from the public internet. It has to be another application or client running within an AWS VPC. So you've got a layer of security right out of the box with that. Data is encrypted by default at rest. So when it's persisted in the database, it's encrypted, and it's encrypted in transit. So using TLS. So you've got those levels of security and encryption. And in terms of compliance, we support and are compliant with a number of different things like HIPAA and different ISO standards. This fifth one there, the same code, drivers, and tools you use with MongoDB. So I said I'd talk a little bit more about what that with MongoDB compatibility means. So, to be clear, DocumentDB is not, like a managed MongoDB under the covers or anything like that. So what we did is we architected a cloud-native database, and it implements the Apache 2.0 open source MongoDB 3.6 and 4.0 APIs. So what that means is, you as a developer connecting to DocumentDB using your existing Mongo SDKs or tools, right? You can expect the same responses back from DocumentDB that you would get back from MongoDB, because the service implements those open source APIs. And then lastly, it's deeply integrated with other AWS services. And we'll see that a bit more in the demo. But just things like secrets manager. Right? So you can securely store credentials and things like that for the database. Right? So the applications don't have to be passing them back and forth. Things like, anyway, can't think of them all off the top of my head. So you'll see them in the demo. Apologies for that. All right, so the architecture with this separation of storage and compute, where you start to see a lot of interesting capabilities. So at the top of the diagram, you see the compute layer. We see in this example, there's 3 instances. There's primary, and there are 2 replica instances. So in terms of compute, a DocumentDB cluster can have as few as 1 or as many as 16 instances. There's always 1 primary and 1 to 15 replica instances. Each of those instances can vary in size, from a relatively small like development instance with 4 gig of RAM and 2 cores, up to our largest instance that we support with 96 cores and 768 gig of RAM. And there's half a dozen or so other instance sizes in between. And then in terms of the storage layer, you see that as a separate box along the bottom. So in DocumentDB, it's implemented as a distributed storage volume. And so it's not just storage. I mean, there's intelligence in there as well. But the takeaway I would say for you to understand is that storage volume is going to always maintain 6 copies of your data across 3 availability zones. So whether you just have a single instance or 16 instances in your cluster, your data is highly durable. In DocumentDB, you've always got those 6 copies of it across the 3 availability zones. And that storage volume scales automatically. So currently the smallest size is 10 gigabytes. The largest size currently is 64 terabytes. So you can go up to a very large data set without having to shard your cluster. Right, you could, in theory, have a 64 terabyte data set with just a single compute node, and that's fully supported. And now because of the separation, right, each of these can scale independently. We've talked a bit about the storage scaling, about like with compute, if you need to add additional instances to support more read workload, all right, regardless of the data size, you can add one or more nodes in about 8 to 10 minutes because there's no data to move around. All the data is in that distributed storage volume. Same way with failure scenarios. Say like if a node fails, the service is going to detect that, automatically replace it. Again, it'll take about 8 to 10 minutes to get that new node up and running because there's no data to move around. So again, regardless of the data size. Okay. Now in terms of actually connecting to the cluster from a development standpoint, going back to the MongoDB compatibility, right, and the implementation of the 3.6 and 4.0 APIs. So we recommend connecting to what we call the cluster endpoint in DocumentDB. There's a couple of different endpoints. One is cluster, and that's, just think of that as a CNAME record that points to whatever the primary instance is. So we recommend using that to connect, because if your primary instance should happen to fail for some reason, the service is going to spin up a new primary. That CNAME is going to be updated in the background and your application doesn't have to change. So recommendation is always connect to the cluster endpoint, connect in replica set mode. So if you're familiar with replica sets in MongoDB, right, same idea here, connect in replica set mode, and we recommend connecting with a read preference of secondary preferred. So if you do all of those things, all right, your client application is, through the SDKs, is going to basically be able to discover the topology of the cluster. As nodes fail and come in and out, scale up and down, all right, all of that is handled for you automatically through the SDKs. And your reads are going to be directed to the replica instances while the writes go to the primary. So your primary is freed up to handle all your write traffic. Replicas are handling the read traffic. Okay, and then a particular feature I want to spend just a few moments on is change streams. So it's implementation of MongoDB change streams. So if you're familiar with change streams in MongoDB, change streams in DocumentDB, all right, you understand what it is. But if you're not familiar with it, just basically it's a time-ordered series of events that occur on the data in your cluster. So it could be at the entire cluster level. It could be at a particular specific database within your cluster, or a specific collection or collections within a database within the cluster. All right, so you got some granular control of what events you want to basically respond to in these changes as they occur. So the default retention of this data is 3 hours. We can maintain up to 7 days worth of these change streams. It's all configurable. But basically what this allows you to do now is you can create applications that can read the changes and take action on that, right? So for every create or update or delete, there's going to be a corresponding event that your application can now be aware of and take the appropriate action. And in this case, we are using that to move data into OpenSearch, right, to enable full text search on that JSON data. But in general, it's wide open, right? You could use in this case, we're using a Lambda to do that. So you could have a Lambda to write data to S3 or move it to Redshift, or pretty much do anything else that you may want to do with it. Okay, so that's just a brief introduction to DocumentDB, and we're going to see it in action here in a little bit, but I'll turn it back over to Kenny here for an overview of OpenSearch, and then we'll get into the demo.
Yeah, thank you very much, Doug. Yeah. So we've taken a look at DocumentDB. Now let's talk about OpenSearch, because both solutions, both services are what we couple together to build out the solution that we're looking at today. So there are a lot of people that are more qualified than myself to speak about OpenSearch. It's considered to be an analytics service at Amazon, but Doug and I focus on databases, NoSQL databases, but we'll see how things go in terms of giving you a 10,000 feet overview of OpenSearch, and also we'll dive deep on a couple of important concepts. So just as an introduction, OpenSearch is a fully managed AWS service that helps customers address the need of running search and log analytics in the cloud. So OpenSearch is a distributed open source search and log trace analytics suite used for a broad set of use cases like real-time application monitoring, log analytics, and website search. OpenSearch is able to work with large data volumes, and it's integrated with visualization tools. It has OpenSearch dashboards, and it supports Kibana dashboard as well from version, I think, 1.9 up to 7.10.2. And it's also integrated with Logstash as well. And within the OpenSearch service, it's also important to know that OpenSearch still supports Elasticsearch versions from about 15 of those Elasticsearch versions before 7.10.2. So you probably heard about the background of the name change. OpenSearch used to be called Amazon Elasticsearch, but late in 2021, we renamed the service to Amazon OpenSearch because the licensing by the parent company for Elasticsearch, the licensing terms was changed, and what we did was to create a fork of the last OpenSearch version of, last open source Elasticsearch version, which is 7.10.2, and then that is what Amazon OpenSearch is based off of. And is also, again, it's not just the OpenSearch itself. It also includes OpenSearch dashboards, which is based on Kibana as well. So OpenSearch is community driven, and a lot of companies like SAP, Capital One, Dow Jones, Logs.io, Red Hat have expressed interest in joining the project to help develop OpenSearch in addition to Amazon. So just a high level of the service, OpenSearch makes it easy for you to perform interactive log analytics and real-time application monitoring. So if you need to do things like application monitoring, as I mentioned earlier, and for things like website search, OpenSearch is a good solution for that. And as I mentioned earlier, supports 19 versions. Actually, I said 15 earlier of Elasticsearch. So that's from 1.5 to 7.10. And it also has visualization capabilities powered by OpenSearch dashboards and Kibana dashboards from 1.5 to 7.10 versions. So talking about some of the benefits of using Amazon OpenSearch or the features, the first one is it's community driven and it's open source. So you can create your own, run OpenSearch on your own by downloading the open source version and running it on your own instances. And also, you could run it as a managed service on AWS through the Amazon OpenSearch service. It's important to make a distinguish the two, the OpenSearch service and the OpenSearch project, which is open source project. So it also includes built-in OpenSearch dashboards and Kibana from 1.5 to 7.10, as I mentioned. Is fully managed. With Amazon OpenSearch, you can deploy in minutes. The service simplifies management tasks such as hardware provisioning, software installation and patching, failure recovery, backups, monitoring, and all those typical what we call as heavy lifting, because when we talk about running search at scale, managing the infrastructure, creating the cluster, and selecting the total number of nodes, things like replication factor, things like data tiering, all those things are available on OpenSearch as a fully managed service, and they are available via the click of a button. And if you had to do that on your own, there's a lot of heavy lifting there, requires a lot of specialized knowledge. Things like sharding, for example, determining the number of shards you want to maintain for every index on your Elasticsearch or OpenSearch cluster. It's a little bit of an art, so using a fully managed service helps you to focus on the more important things rather than the repetitive tasks. And given that also we run it at scale for multiple customers, all the best practices are also implemented as part of the service. Things like zone awareness, for example, is another. So it's secure and compliant, what you will expect from any AWS service. Security is our job zero. OpenSearch service takes care of the security patches and offers network isolation via VPC, just like Amazon DocumentDB, fine-grained access control, multi-tenant support. Speaking about multi-tenant support, there are many different strategies that you can use for running multi-tenant applications on Amazon OpenSearch. You could decide to keep each tenant separate index for each tenant, or you maintain separate type for each tenant, or you create a completely different cluster for each tenant. There's a deep dive talk around tenancy strategies that by one of the OpenSearch specialist essays, I think John Handler. You should watch out for some of his talks if you really want to go really deep into OpenSearch. Also, that operational overhead that we talked about comes with a cost as well. So running a fully managed service like OpenSearch helps you to eliminate that operational overhead and reduce the costs with automated provisioning, software installation and patching. All those things help you reduce cost of management and also helps you to be able to optimize your OpenSearch installation. And we also have things like storage tiering as well. So with Amazon OpenSearch, there are multiple. There's the hot data tier, which is on the instance class. You could also use EBS volumes for your hot data tier. And you also have the ultra warm and then the cold storage tier that you can move your data across to. And that also helps with cost optimization. And then we don't have this on the screen, but it's also tightly integrated with other AWS services. This is one of the benefits. So things like seamless data ingestion from DocumentDB, for example, and then we also have things like Kinesis data stream that you can integrate with Elasticsearch natively. It integrates with CloudFormation, CloudWatch for your monitoring, and AWS Lambda for writing your documents or objects into Elasticsearch. And then other third-party tools like Logstash as well, so that you can store your raw data or your raw log files and generate actionable insights quickly. Today's talk is more focused around the search use case, but it's important to know that Elasticsearch is also very, very useful for log and trace analytics, and especially with Kibana dashboards. So how does the service work? This is very, very high level again. There are different things that we could talk about, like replication factor, things like, when you create your domain, the clusters, etc. But high level how it works. Before I talk about this one, OpenSearch, which is based on Elasticsearch, which is also based on another open source technology called Apache Lucene. So Apache Lucene is kind of like a Java library that provides very, very powerful search functions. And the person that actually originally created a solution that led to Elasticsearch was actually setting out to build a search engine for his wife's recipes. And he ended up building a tool called Compass. He didn't build that search engine for his wife, but he went and did it at the office and convinced his company to build that Compass. And then Compass kind of evolved into Elasticsearch, which is kind of a wrapper on top of Apache Lucene, which is obviously a Java library, much more complex to use. So Elasticsearch is kind of REST APIs on top of Apache Lucene. And in addition to that, management of the clusters, distributing data across nodes, all of those things are provided via simple APIs, and that's why Elasticsearch and by proxy OpenSearch is very popular and powerful. So the purpose of this diagram is to explain how OpenSearch works at a high level. So data gets sent to OpenSearch in JSON format, and then it is indexed. So with OpenSearch and Elasticsearch, it's very easy. You don't need to create an index when you are using OpenSearch. If you just start write data into it using the put HTTP request, an index is automatically created for you. So it was actually very surprising for me to see how easy it is to use the service. And then the data is indexed. All the fields in the index, all the fields are indexed. So if you wanted to do that on any operational database where you index all the fields, we all know what that you have storage implications. First, your database size will be very large, and you don't want that because potential performance drawbacks. And then for some database engines, you have to load all the indexes into memory as well. So, but with a specialized service like OpenSearch, you can index all the fields within your documents, and everything is searchable. And in addition to that, there's also more advanced capabilities like natural language processing, fuzzy search, pattern matching, stemming. So let's say you were searching for something like swimming, you get results that include things like swim. Or if you were searching for a phrase, functionalities like search as you type, for example, where as you are typing, you start seeing some results. It will be very difficult to find, a native database. I call Elasticsearch a data store, but a native database, I'm talking about MySQL, DocumentDB, MongoDB, DynamoDB, to have those kind of functionalities. But OpenSearch and Elasticsearch does. So when you've indexed your data, all the data is indexed, then you also use REST API calls to get your data from the Elastic OpenSearch cluster, and you can do many different things there, aggregations, pattern matching, etc. So OpenSearch works with structured JSON containing fields and values. So DocumentDB stores JSON documents natively. So it also pairs very easily with DocumentDB, because if you were using Postgres, for example, you would have to install a plugin called Wall2JSON, and then maybe that you will use that to write into your Postgres streams, if whatever implementation of your Postgres support that, to write to Kinesis or something. But with DocumentDB, because data is stored natively in JSON, you can easily just integrate it with Elasticsearch. So here's the data lifecycle in OpenSearch. I kind of touched on this earlier. So when you index your data, it goes directly to to the hot data tier, and which is very fast because that hot data tier are sitting on the instances. So the instance stores are where your data is stored. They are data bearing, but you can also use EBS volumes as well for additional storage. And then after that, you can migrate the indexes within your OpenSearch cluster to ultra warm and cold storage for long-term low-cost storage. And then in cases where the data is no longer needed, they can be deleted or moved to maybe archived to like S3, Glacier. So with that, we'll move to the demo, and I will hand over to Doug to show the demo architecture and then give a little bit of brief demo on how to integrate DocumentDB with OpenSearch.
Yes, so can you all hear me? Okay, now we're getting close. So I've got a couple minutes. I'll be pretty abbreviated a little bit, but just try and touch on the what I want you to take away. So what we've built out for this is what you see here. We got an AWS Cloud 9. That's a cloud-based integrated development environment. So we got that set up where it can connect to a DocumentDB cluster and have inserted some data into it. We're using a Lambda function to read the changes from the change stream being published by DocumentDB, and then basically write the corresponding document into OpenSearch. And the way that Lambda is triggered is we're using Amazon Event Bridge, and that's configured to just every minute go ahead and create an event on a simple notification or SNS topic. And the subscriber of that topic is the Lambda function. So basically, every minute that Lambda function is going to fire off, hey, is there anything on the change stream? Let me read it, update Elasticsearch appropriately. And the thing on the bottom that I'm not really going to show is Secrets Manager, and that's where we store all the credentials for DocumentDB, right? So you can safely store the master username, password, and things like that. So I got, let's see here. Let me safely store the master. All right, so what you see on the screen here is just a sample of some of the data in the DocumentDB cluster, and this is a tweets data set that we've got that we use in some of our examples. But you see there's a lot of text there, and MongoDB has a regex operator. DocumentDB supports that as well. So certainly you could do some regular expression type matching on the data, but it's nowhere near as flexible as like what Kenny was talking about with OpenSearch, right? Where you can do things like word stemming, fuzzy matching, searching for basically misspellings and things like that. That's the fuzzy matching. So extremely difficult, if potentially impossible to do, all right, with regex operators that are supported. So here's the event bridge, the schedule, right? Every minute it publishes an event to a simple notification service topic. All right, and we see that the subscriber, so that is this Lambda function. And what I'm going to do, probably all I have time for, is I'll show the code, all right, and just show really how easy this is to do this integration. So just kind of walk through the code. The way this Lambda function is written, first thing it does, it connects to the Elasticsearch target, or OpenSearch target, connects to the DocumentDB source, and then basically it gets access to the change stream that has been enabled. All right, and the way you can enable change stream, you see there, just using standard Mongo shell command to enable the change stream. That gets access to that change stream, and then every time it starts, this particular Lambda is configured to read no more than 1,000 documents from the change stream at any time, as we see down here. So as we're reading in the Lambda, we look at the operation type. So the event indicates what the operation was. Right? Was it an insert or an update or a delete? So if it's an insert or an update, we just simply call using the Bodo3 Python SDK, call the index API on Elasticsearch. So it's going to go ahead and index that document. Right. So as soon as that's done, now I can search that in Elasticsearch. And if a delete event occurs, document was deleted from DocumentDB, this is going to handle that case. It's going to go ahead and actually delete the corresponding document from OpenSearch. So that's, again, not a lot of code to be able to do that integration. So now you're able to do those very rich full text searches on JSON data that you've got in DocumentDB or MongoDB for that matter. Okay, and I know we're out of time. The other presenters are outside the door, so just I'll go ahead and leave this next step slide up here as a call to action.
Yeah. Really quick here. So search is an essential part of many modern internet scale applications. So a trend that we see is in NoSQL and relational databases is the mainstream adoption of document or JSON model. Services like Postgres also have like plugins that can allow you to store JSON document natively. So a lot of developers are building with JSON. And then another key takeaway is that you can integrate Amazon OpenSearch with DocumentDB using change streams like Doug showed in the demo. And that helps you to be able to power search queries at scale over your JSON data that's stored in your document store. And then you can also use change streams, to integrate Amazon DocumentDB, not just with OpenSearch, but also with other AWS services like MSK, Kinesis DataStream, SQS, and S3. And with that, we are ending the talk. Doug and I will be outside the room to take any questions. Thank you very much, everyone.